Now that we know what it means to solve a differential equation, let's talk about how we might go about solving a differential equation. Now, it turns out that there are two main types of methods that are used to solving them. First is to use essentially an educated guess. So I call this method guess and check. And so as an example, let's say that we have the equation y double prime plus 4y prime plus 3y equals 0. We'd like to find a solution to that equation, and we don't have a clear intuition about how we would go about solving for y directly. But what we can do is come up with a guess. In this case, I'm going to guess that y is going to be some exponential function. So I'm going to guess that it has the form e to the mx, where m is some number. Okay? Let's see what we can do with that. So we'll try plugging that expression in, taking the derivatives, and seeing under what circumstances that satisfies the equation, if any. So let's compute y prime. Notice if we apply the chain rule here, we'll get an m out front. And if we take a second derivative, we'll get another m. And so if we plug into the equation, we will have y double prime is m squared e to the mx plus 4 times y prime, which is m e to the mx, plus 3 times y, which is e to the mx. And you'll notice that each of these terms has an e to the mx in it, and so we can factor that out. And we'll be left with m squared plus 4m plus 3. And so the only way that that solution works is if e to the mx is equal to 0, or that polynomial in m is equal to 0. And it's straightforward to convince yourself that the exponential function is never 0, and so we can conclude that this is 0. And that gives us some choices. Let's see. We could either use a quadratic formula to figure out for what values of m that's 0, or we could just factor. In this case, it's easy enough to see that that's just m plus 3 times m plus 1. And so that's 0 when m equals -3 or -1. So we came up with a guess for the solution. We hypothesized that it's an exponential. And at this point, I didn't give you a lot of reason for why that would be a good hypothesis. When we get later on the semester, we'll talk a little bit more about how do you choose an appropriate guess. But for now, we'll just take that for granted. And so we plugged it in and then checked to see the circumstances under which that guess is valid. And it turns out that there are only two choices for that growth rate in the exponent m. M has got to be either -3 or -1. So we could say y equals e to the -3x is a solution, and y equals e to the -x is a solution. And in fact, it turns out that the most general solution is actually a linear combination of those. So if we put some arbitrary constant a times one of the solutions plus some arbitrary constant b times the second, you can check this if you take your derivatives that will indeed satisfy the equation no matter what a and b are. So the good news about differential equations is that although it is sometimes hard to find a solution, it is easy to check if we have a solution by simply plugging in, evaluating the derivatives, and simplifying and checking to see under what conditions the left and the right hand sides of the equation are equal. So guess and check is one method for coming up with solutions. Let's do another example for our second method. And the second method is going to involve integration. So perhaps this should not come as a big surprise to us. If you have an equation with a bunch of derivatives and you'd like to get rid of the derivatives, well, the natural thing to do to get rid of a derivative is to take an antiderivative. And we know from calculus that the antiderivative of f prime of t dt is always just the original function plus a constant. Or if we want to use a definite integral, the integral from 0 to t of f prime of some dummy variable tau d tau. And this comes from the net change theorem, but you can show that this is just f of t minus f of 0. So you can use either antiderivatives or indefinite integrals or definite integrals in the second case to get rid of derivatives. And so for certain differential equations, we can just integrate directly to find the solution. So suppose we have the equation y prime equals e to the t. That's a differential equation. We don't know y directly, but we do know something about its derivatives. And if we wanted to find y, we could then integrate both sides. I will use the second formula, the integral from 0 to t of y prime of tau d tau. So if I apply an integral to the left side, I'd better apply an integral to the right. And if I integrate both of those sides, let's see, we said the left-hand side, that just must be the difference between y of t and y of 0. We've applied our theorem there. And we need to use an antiderivative of e to the tau. And in this case, I made it nice. The antiderivative of e to anything is just that original function. So we just have e to the t minus e to the 0, which tells us that y of t equals y of 0 plus e to the t minus e to the 0, which is 1. Now, something interesting to note there, we have this y of 0 left in the equation. And what that suggests to us is that, like the previous example, the solution to this equation is not unique. There's more than one function that satisfies this relationship. In fact, we could choose any value for y at 0, and we would still get a valid solution to the equation. Okay, so to summarize, there are two main families of methods for solving differential equations. The first uses some sort of educated guess, and then we check to see when that guess works. And the second uses integration. Now, the bad news is that this sort of method doesn't always work. If I change my equation ever so slightly, let's say I added a y to the equation, then you'll see that this method of integration is going to fail, because although I can integrate this side, that's no problem. On the other side, I have this y to deal with, and I don't know the antiderivative of y. So we're going to need a little bit more clever of a method before we can just apply an integral. But thankfully, there are some techniques for doing that, which we'll get to in the next few days.